Hi, I am Alper Ahmetoğlu and I will present our work Hierarchical Mixtures of Generators for Adversarial Learning. Generative adversarial nets are composed of two networks called the generator and the discriminator. The generator tries to transform a predefined distribution P of Z into P of X, which is the distribution that we want to approximate. The discriminator, on the other hand, tries to discriminate between the real samples and the fake samples. At optimality, the discriminator cannot tell the difference between the real and the fake as the generator successfully models the distribution. Although this is appealing, there are problems regarding the training of GANs. The first is the gradient backpropagation problem. Depending on the choice of the loss function, gradients either vanish into zero or their amplitude and variance becomes too high to a point that makes the training impossible. And the second is the mode collapse problem, where the generator fails to model some parts of the distribution. In general, there are three different solution approaches to these problems. You can change the architecture so that the networks become easier to train. You can change the objective and minimize the divergence or distance other than Jensen-Shannon divergence. For example, in our experiments, we used the Wasserstein distance. Or we can apply different regularization techniques to control the gradients. Our approach falls into the first category, that we propose to use multiple generators instead of one, so that each generator can focus on a different mode of the data. There are several works that use multiple generators. The main difference in our work is that we use a hierarchical soft mixture of multiple generators. Such an approach allows us to interpret the data hierarchically. We propose hierarchical mixtures of generators inspired by hierarchical mixtures of experts. Let us go over the algorithm. We have a binary tree with decision functions on the nodes and generators at the leaves. At each iteration, starting from the root node, we calculate the gating value. This is a simple logistic unit. The output determines the weights of children nodes. The same computation is repeated until we get to the leaves where we have the generators. Here, generators are linear projections, but can be any differentiable function. Although there seem to be lots of computations, we can compute these in parallel since they are independent of each other and utilize the hardware. After we compute all nodes, we mix the generated samples with corresponding weights up until the root to get overall response of the model. This modification is only for the generator. The discriminator architecture remains the same. Now, instead of using a hierarchical mixture, we can also have a flat mixture of generators by replacing the sigmoidal unit with the softmax function. We first made an experiment on two-dimensional Gaussian mixture data and compare our method with other methods that also use multiple generators. Here, the blue points are the real data and orange are the generated ones. The response of the discriminator is shown in the background as a grid, where the red is high and the blue is low. This animation shows the outputs at different training stages. As you can see, Hmog and Hmog cover all modes of the data. After training, we analyze the response of each generator. On the right, the Hmog model divides the data into two at each level of the tree. At the leaves, we can see that each generator is responsible for a different region of the data. Next, we made experiments on 5 popular image datasets. As using convolutions for image generation is proven to be useful, we also used a convolutional network on top of the response of the Hmog model. The discriminator here is also a CNN-based architecture. Here, we show the FID scores and 5 nearest neighbor accuracies versus the parameter count, which corresponds to the number of generators employed. FID scores should be low and 5 nearest neighbor accuracies should be closer to 50%. The results show that Hmog and Hmog models perform better than other multiple GAN variants. We also trained a single generator model with a fully connected layer instead of augmenting multiple generators. This is shown in blue in the figure. We see that using multiple generators indeed increases the quality of the samples. Here are a couple of generated examples from the Hmog model with 16 generators. One advantage of using Hmog over other models is that it provides a way to interpret the data hierarchically. For example, here for the MNIST dataset, we show the average responses of each node in the tree over 10,000 samples. And at the leaves, we show the 5 most probable responses for each generator. The root node shows the average of all generated samples. As we go down in the tree, patterns emerge. Even though the training is unsupervised, we can see that each generator converges to a specific digit or different variations of it. These gating units let us understand the specific job of the generator, which can be useful when we want to sample from a specific part of the distribution. If we want to understand the specific job of a node or want to sample from a specific part of the distribution, What we can do is draw a sample of input noise vectors, freeze the network, and update the input with SGD to maximize the activation of a specific path in the tree. Here we show the response of each node in this manner. You can also maximize the combination of two paths instead of one to mix the features of two generators. In this animation, we show the response of each gating value together with the generators at the leaves for the syllabate dataset. This animation essentially shows which part of the tree was responsible for the generated sample. To sum up, inspired by hierarchical mixtures of experts, we propose hierarchical mixtures of generators. Hmog performs better than other multiple GAN variants on toy experiments and 5-image datasets. Hmog is a general formulation and it can be integrated with other GAN architectures. Hmog is interpretable to some extent and it provides a way to understand the data in a hierarchical way. You can download the PyTorch implementation and use it. Thank you for your time. Questions and comments are welcome.